Hello. I was thinking of ways how I could demonstrate the use of ECAD, and one of the things that I took on board from something Bob said was he wanted to embrace the use of modern technology, particularly to deliver lessons via Skype. And with that in mind, I thought I'd do something different. Rather than pages and pages of text with screenshots, I thought I'd rig a bit of equipment up and show you firsthand what I use ECAD for on a regular basis. If you see the screen in the background, and I'll zoom into that, this is one of the packages I use. It's called Proteus. It's a very useful tool. It does quite a few things. Now on the screen you can see this is just a 3D visualization of a circuit board that I made some time ago. It's called the Barlow board, and it's something I've been working on for quite some time. I've actually moved forward with this. I'll not get too much into it, purely for the reason that it's not really salient to what I'm doing today. But that board is actually that board that I've made up. Now, Proteus is more than providing pretty 3D visualizations, although that's really good for sales literature and to give you an idea what the finished product's going to look like. From an ECAD perspective, it's not really relevant. It doesn't. It's not part of the design process. It's more to give you a feel of what the product will look like. The key thing to Proteus is it's got a schematic editor, schematic capture. Now, this is not dissimilar to any of the other packages, multisim for one, in that you place components, connect them together, and you can run simulations. What is different though is you can place microprocessors. Now this one I've got sat here is the PIC16F690. It is the same processor as that there, which is the PIC16F690, and obviously you can place that in your circuit and perform simulations on it. Now a PIC out the box doesn't do anything. It needs to be programmed. You need to tell it what to do. So a good thing about Proteus is it has a source code editor, and this is the code I wrote to control my Barlow board, which is essentially it's an I/O module, but it's a clever I/O module. It takes a variety of inputs and it will give you different outputs depending on the settings via the dip switches. So just to show you. By whatever you have these dip switches set at, will give you different outputs, i.e. timed outputs, latched outputs, whatever you tell it that you want. So the beauty of Proteus is not only can you simulate the circuit, you can actually simulate the microprocessor as well. So I've wrote this code, and when I run a simulation in the schematic capture, it actually runs as it would with my program. Now, there is a limitation to this, and well, I say a limitation, it's actually a few bugs that I found in the program. Certain components won't simulate very well. So when I've placed these components match, i.e. manufacturer product code, they match perfectly to the components that I bought in real life. So the theory behind that is whatever you simulate on here is a true like for like. It is what it's going to be when you build it in real life. Unfortunately, because some of the components don't simulate very well in Proteus, I find it quite ironic. You actually have to sort of fudge the simulation, if you like, to get it to run. It's a bit of an annoyance. A perfect example would be these relays here. Those relays are animated generic relays in the library of Proteus. The reason I've had to use generic ones is the real ones won't simulate. Now you can download updated component libraries. I can't find ones for these relays that I've chosen, and I'm sure if you let Proteus know, they will they'll issue a fix. It's a problem I find quite often. It's just something we have to live with when in the Proteus environment. So that's a very brief summary of Proteus. One of the other things it does is it has a PCB layout. Now the PCB layout, you place your components, move them around, set your traces where you want them to be, and when you're happy with that you can generate a Gerber file which you then send to a board house, which I did. The board I showed you earlier, that's the etched version that I've had done. Now you'll notice I said etched. It's nothing to do with ECAD. It's because when I'm doing prototypes I only buy low volume quantities of boards, and it's cheaper to have them done in the UK via etching service rather than the other methods used for PCB manufacture. When we go into mass production even, we'll be sending the Gerber files over to China and having them shipped out via a Chinese company when we're having 1,000 plus made. But for now, the Proteus generates a Gerber file which is perfect for the etching company we use in the UK. So that's Proteus. While we're talking about PIC controllers, the next thing I want to show you is another way to program the PIC. Now, strictly speaking, this is an ECAD, but it's very closely related, so I'm going to show you. It's using Microchip's own in-house compiler, the XC8, and also MPLab to write the source code. So as you can see, this is an exact copy of the source code. And the reason I'm mentioning this is I've had problems with Proteus in that compiling the code onto the PIC kit, it doesn't always compile very well. So what I've got into the habit of doing now is I use Microchip's PIC kit. I compile it onto the PIC kit, which is this unit here. This is bought for about £30, the PIC kit and the demo kit. And as you can see, this chip here, I can program using the PIC kit using MPLab. Once I've programmed it, I remove the chip from the demo board and then insert it into my circuit board, my prototype I've made. Originally, I designed this so that I've got a 5-pin header, and the idea was to program straight onto the board like that. For some reason, it wouldn't work. I've not got to the bottom of that yet, but in order to continue with the prototype, I've cheated a bit, and I use the Microchip demo board, and then I just simply drop the PIC onto the board. So I'm not going to go too much into MPLab because technically, like I say, it's not ECAD, but I use it symbiotically with ECAD. It's a very, very important tool, and I thought it was appropriate to mention it. Circuit design, for instance, the Barlow board mentioned earlier. You'll recall that the Barlow board was designed in Proteus, and the code for the PIC controller was written in C, and we could compile that in Proteus and debug and test and simulate, albeit with a few minor bugs, which I spoke about earlier. There's a variance of ECAD that not only can we debug, but we can actually write a program for a PLC. And there's a few different versions, but the one that we use is it's a copy of the Siemens X logo. It's called an X Logic, and that's an industrial grade PLC, albeit a mini PLC. And we use a software package to not only write the program but debug in real time. I'd like to show you a project that I was working on some months back. It is actually a live project. The system's been installed. We installed using relays, and then I decided to improve on that design, and I've done a demo where we've used a PLC to demonstrate the benefits of using PLC. Designed a few months ago. It is actually a live job in that we have something very similar to this installed on site. This is an improvement that I proposed to the original installation. The original installation used relays as the control logic. It worked, it was fine, but it wasn't great, it was clunky and very difficult to service. The reason this is relevant to ECAD is inside this, which I'll show you in a moment, there's a PLC, and that PLC was programmed and debugged using ECAD. In fact, there was quite a lot of debugging because it didn't work originally, and there was a lot of simulation and debugging to find out where the problems were. I'm not going to go too much into what this does and doesn't do because that isn't relevant to ECAD. I'm going to give you a brief demonstration purely so you know roughly what it is, and then I'll show you the PLC and you'll see what what role the PLC is playing. So this is an electric fence interface. It's an interface and a representation of a front end. Now normally they'd be two different things. Because this was a proposal to a customer, I built this panel as a demonstration panel, and for simplicity I integrated everything together just purely so I've got one unit to show them. As you can see, this represents the fence boundary and it's broken into different zones. Now I can arm each zone individually with these buttons down here. Obviously normally that would be a keypad or a key fob or something like that. You wouldn't have a security system controlled by buttons. And I can also introduce faults onto each individual zone. You've got status indicators, which will let the customer know what the status of each zone is, whether it's an alarm, whether it's arming, what it's doing, or whether it's safe to enter, which is green. And on site we've also got traffic lights. On site they're positioned outside each gate, as you can see as this representation here. There's traffic lights adjacent to each gate. I created a mini model of them just so it is a true representation. So just like any security system, I can arm individual gates, individual zones. So let's say I want to arm zone 3. We give zone 3 a signal to arm. Now as you can see, zone 3 indicator has gone solid red, indicating that that zone's armed and live. There's 10,000 volts flowing through that zone, obviously on site, not in this thing. And this particular customer wanted an indication that some of the system was set but not all. So that indication was flashing red. When the whole system's set, that will go solid red. So if I arm the entire system, you'll see they've all gone red. We've got 2 flashing reds on the gates. That's giving the customer a time delay to get out. Now on site that is 60 seconds or whatever. On this particular system, because it's a demo system, I think it's 5 seconds. So as you can see, all the zones have gone red. Now like any security system, when it's armed, if there's a breach in that zone, it will set an alarm off. So let's breach zone 3. It sets the alarm off. Now, due to noise regulations, you can't have that sounder going off indefinitely, so the sounder will stop after a period of time. In this instance it was 5 seconds, but on site it will be something like a minute or 5 minutes or whatever that may be. But the customer also needs an indication when they go back to work the next day that the system's been an alarm. So as you can see, the janitor panel's saying zone 3 was an alarm, and it will stay like that until the customer resets it. So we'll remove the fault, which I already have done, and then when we unset all the relevant zones, the system goes back green again. And that's essentially how an electric fence system's controlled, or certainly this system. So let's look under the hood. Remove the cover. Inside you can see the PLC that's controlling everything. I'll zoom in a minute, but briefly up here, this is obviously all the control buttons and the indicators, LED indicators on the main screen. Not really that important for this, so let's zoom in and we'll look more closely at the PLC. So what we've got is we've got a programmable logic controller. It's an industrial one, albeit it's a mini PLC. You get much larger ones than this. It's got expansion modules, so that was purely because of the amount of inputs we've got and outputs. There wasn't enough on the PLC unit itself. The PLC can't be programmed on its own. It needs to be connected, which you can see, which is this wire here, connects it to a PC, and that's where ECAD comes in. The ECAD's used for programming it. What you can do is, if you have any timers or anything like that, for instance we had the alarm was timed for 5 seconds, we can actually change the time on the PLC itself, but any of the major fundamental programming has to be done using ECAD. That's it for what's under the hood. What we'll do now, we'll look at ECAD, we'll look at the program and how it was all put together. ECAD come in. Well, as you can see, this is a digital representation of the PLC I've just showed you. And the beauty of this particular software package is you use function blocks. Now, programming with function blocks is so much easier than programming with C. You quite literally drag and drop the various different function blocks depending on what you want. These represent inputs, these represent outputs, and then you've got various different logic in between, timers, flip-flops, on delays, off delays, repetitive white relays, those sorts of things. And the beauty with this thing is you start at the beginning and then you expand on from there. So straight away you create all your inputs, create all your outputs, and get one input doing roughly what you want it to do. And then you can debug in real time. So for instance, we had a problem, well, we had a few problems, but the main problem was at certain points of the program it got locked up in a never-ending cycle. In fact, it was around here somewhere, I can't remember exactly where it was. Whereas that, depending on a certain combination of inputs, it was a never-ending cycle. You couldn't break that cycle without powering the unit down. And in a self-contained security system that's supposed to be self-resetting, having to power the unit down isn't, well, it's just not done. So the beauty of this is you debug in real time, so the debug process is part of the design process, if you like. But then when you're finished, if you haven't connected all your peripherals, you can actually test what's happening in virtually. I can virtually trigger these inputs. Even better than that, once you've got the actual hardware, which we have, we can get the software communicating in real time with the hardware. So if it works in simulation but doesn't work in real life, you can run the hardware in real life and monitor the software to see what it's doing. So I'm going to press some of the buttons on the panel I showed you in the previous video, and you'll see various different inputs and outputs coming on. So I'm now turning several zones on, and as you can see, various different inputs are lighting up and going off as I'm turning off the zones. It is an extremely useful piece of software. It's not full-blown ECAD, it's not circuit design, but it does fall in the ECAD bracket in that you could not program that PLC without it. It's electronic and it's computer-aided design, so I think it's very relevant that I showed you this, because this does fall under the banner of ECAD. And as you can see, it is a very, very powerful program. Obviously, that the demonstration unit I showed was a improvement of a live site that was using relays. Now it works out quite nicely that I can show you the schematic for the relay system, because that was designed using Microsoft Visio. Now Microsoft Visio isn't strictly speaking ECAD. It is a computer-aided design package, and it does have elements of electronics in there, but it isn't widely used for circuit design or anything like that. It just isn't powerful enough. But let me show you the schematic. So this is exactly the same system that I showed you before. Obviously this is the Mark 1 if you like. What I showed you in the video was Mark 2, that used the PLC. As you can see on this, there is no PLC on this. It's the same circuit, does the same job, but instead of the buttons you've got the input from the alarm panel, the third-party alarm panel, and you've got a lot of banks of relays. Now these are just standard changeover relays. These are TTL state changing relays. They change a TTL input to a normally open, normally closed signal, and then you've got the actual panel outputs up there. Visio is great, as you can see over in this corner, and you've got the various different contacts, this, that and the other. It's okay, I use Visio a lot. It isn't strictly speaking ECAD in that you can't really design much, but you can do nice schematics, as you can see here. So I'll just, that was Visio. I'd like to show you a photo of the Mark 1 in real life. Now this is actually installed on site. So this is what I use Visio. I designed it first and then I built it. As you can see, it's neat and tidy, but it's not great. In fact, I installed that over a year ago, and we had a fault quite recently, and I opened the panel up and it took me a good hour to try and get my head around what was doing what, and it was me that designed it. So that just shows the complexity of it, and it's needless. You can't expand on that. The PLC, if you needed to add additional modules to it, it's fully expandable, and the programming's a breeze. Once you've got the main programming, you use the software package to add and take away and amend as you see fit. This, it is what it is. You can't expand on it easily. As you can see, it's a full unit. In actual fact, we had to fit some timers on site because there was an oversight in my design. The timers are there, and retrofitting those on site was a nightmare. Whereas if we'd have used the Mark II version, if you like, using the PLC, there's a function block with a timer. It would have just simply been a case of dragging a function block across. So all in all, ECAD's the best way to go, and PLCs and microcontrollers, that sort of thing. Another use of Visio, I mentioned how you can do basic circuit design. There we are. This is a circuit I designed. In fact, I think this is it's an alarm circuit. It uses you can't simulate this, so obviously we've designed it, and it does work. I know it works, but I couldn't simulate it on that, so I can draw the circuit up. But if I wanted to simulate that, I'd have to use another software package, another ECAD package called Cedar, and here it is. So exactly the same circuit. We've got a variety of inputs. I believe they represent door contacts, they represent binary numbers, and that represents a reset button. We've got some binary counters around here, and we've got some binary counters up here, and various two outputs. The beauty of this is CEDA I can simulate. So if I tell the system to arm, it doesn't do a great deal. There we are. So now we're arming. As you can see, the binary counter's counting. Those are just little indicators to make sure the binary is counting correctly. And as I said, this is an alarm circuit, so it's now set, and it's set the alarm. This is an entry. Because we didn't close the door contacts, this is counted down, and that's your entry, and it's now gone off into alarm. So this is exactly the same circuit as what I had in Visio. Visio group the logic blocks up into nice, neat schematic versions, which is what Visio is good for, whereas the CEDA gave me a nice breakdown of what's going off, and you can see clearly how it's working in circuit. A software package called Tina, and if I open it up, there we are. I've got a demonstration circuit there. Now this is just something I've thrown together. It's a bistable multi-vibrator circuit. At first glance, it's a good package. It's very similar to Multisim, Eagle, various different packages where you drag and drop components and you can run basic simulations. The reason we was interested in Tina is it's cheaper than Proteus, and I actually bought this before I bought Proteus. The reason being is it's supposedly had microcontrollers. As you can see, it says MCUs up there. Now it does have MCUs, and if I open it up, so if I open it up, you can see all the various different microcontrollers. You can see the PIC family. I use PIC a lot. I'm not so keen on Amtel or anything like that. It's PIC processors I normally work with, and at first I thought it was a very good package. When I got more into it, I realised that you couldn't inject the C code easily. There is a patchy way around it, but that's not supported by Tina developers. Whereas with Proteus, you can write the C, you can compile the C, and then you can simulate the C. Albeit with there are a few bugs mentioned, and you have to live with that. But with Tina, it's virtually an impossibility. So we bought it because we thought it was better than Multisim. Cheaper than Proteus, but in actual fact it didn't do what I wanted it to do. I've still got the program, but I don't really use it very often. I've just thrown this circuit together. There's nothing wrong with it. It's on par with Multisim, probably a little bit better than Multisim because it has PIC support, but all in all, there's no bells and whistles, nothing outstanding that I can really comment on. Packages that are worthy of mention in an ECAD review. Let's take for example Altium. Altium's arguably one of the biggest, one of the best software ECAD packages about. It's all singing, all dancing, got all the bells and whistles. Unfortunately, it has a starting price bracket of $5,000 US. Hence, I don't have a copy. I can't show it you. I did have a play around with Altium some time ago. I was lucky enough to get a demonstration version. It's a very complex piece of software to use. I think if you use it every day, it's very, very powerful. It's not dissimilar to, say, Adobe Photoshop. We've all used Adobe Reader, but if you was in art and design, that sort of thing, you'd use Photoshop. When you first buy it, it's very difficult to get into, but once you use it, you realise just how powerful it is. I liken Altium to be very similar to that. I couldn't get into using it. Everything was laborious. It was very difficult to use, and it wasn't, the price tag put me off straight away. It wasn't something I ever considered using on a full-time basis. But it was worth mentioning because Altium supports all the families of the PIC range, the Amtel range, the most powerfulest processors. It's got full schematic capture. You can generate your Gerber files. It does everything and more that Proteus does, so it is better than Proteus. But unless you're running a massive design shop like Apple or Samsung or Siemens, some big company like that, there isn't really a need for that sort of power. Hopefully we'll grow into it, and we may have a use for it at some point in the future, but right now Proteus does everything we need it to. I live with the bugs, and I quite like Proteus. Something else worth mentioning would be Arduino. Arduino's a growing market. That's basically a microcontroller, sorry, a microprocessor, and then the peripherals bolt on. More based on programming rather than PLC. It's not something I'd use in the field. I'd use a mini PLC if it was out in the field. Circuit design, I tend to like the flexibility to design my own circuits, like with the Barlow board. It's something I'm going to look at more in the future, but it's aimed more at learning how to program. Very similar to the Raspberry Pi, if you like. That is a mini computer. Not really ECAD, so I'm not going to go too much into that, but Raspberry Pi, something similar to the Arduino. Finally, Q-Block. It's an American company. I did demonstrate Q-Block to start with. It's similar to it's an in-between a PIC kit and a PLC. You basically have test hardware, you buy the relevant ICs, and then you write the program, you compile it using ECAD, and then you load it onto the IC. The problem being is it was kind of overtaken by Arduino, and it's an American company, so the bits are hard to source, so we never really went any further with that. Of ECAD packages to a conclusion, I'd like to mention that engineering isn't about reinventing the wheel. It's about picking the right package, the right solution for each job as you see appropriate, and quite often that's a combination of improving on a previous design or using different packages working together. For instance, when I design in Proteus but compile in the XC compiler, they're two very different proprietary pieces of software that I use together to solve the problem that I have at hand. For instance, if we're designing something on site, more often than not it's going to be quite industrial, so I'll use a mini PLC, then I'll use the Xlogo software. If I'm designing something bespoke, a bespoke piece of circuitry such as the Barlow board or something like that, then I'll use Proteus, or a combination of Proteus and the XC8 compiler. There's no such thing as a perfect software package. We use many different packages as mentioned. We've got Proteus, PIC, XC8, Xlogo, Visio, Tina, Cedar, sometimes Arduino, and Altium, which we don't use as we've mentioned. But each have their own merits and disadvantages. Arguably Altium is the best software package, but at $5,000 it's far too expensive for what we use. So I'd like to finish on saying it's about using the right package or packages for the solution, for the problem that you've got in front of you. And thank you for watching.